So good evening, ladies and gentlemen. My name is Paul Young, and I have the privilege of being the Vice President of Research at the University of Toronto, and it is a distinct honor for me to be invited to join you this evening for the Herzberg Lecture by Nobel laureate Dr. Charles Townes. Dr. Townes, on behalf of the University of Toronto, the Canadian Association of Physicists, and all of our guests tonight, welcome. We are honored to have you deliver the Herzberg Lecture this evening on the 50th anniversary of the idea you and Dr. Scholow conceived the laser. The University of Toronto is also delighted to be host for the annual Congress of the Canadian Association of Physicists. There can be no better speaker to address a gathering of physicists than someone of Dr. Townes' stature. I know Dr. Robert Mann will provide a detailed introduction to Dr. Townes shortly, but let me say that it is scientists and innovators such as Dr. Townes who play an essential role in global society, in fact, moving us forward. The laser is, of course, used in practically every industry. It is the laser at the root of your DVDs and CDs. It is the laser that has revolutionized healthcare. For example, how many of you here tonight has had laser eye surgery? Lasers are also used to scan barcodes of products you buy in retail stores and in smoke detectors in your homes, and they are routinely used now in construction as well as in countless other applications that are essential to our daily lives. Indeed, there is no question that the laser is one of the truly great inventions, one that has literally changed the world. And the man who conceived it is here tonight. Again, what an honor it is to have you with us, Dr. Townes. I should add, as the holder of an honorary degree from the University of Toronto, Dr. Townes already has an association with us. And his research partner in creation of the laser, Dr. Arthur Scholow, earned his PhD here at U of T in 1949. We are proud of our shared history with Dr. Townes and Dr. Scholow, and we are delighted to build on that history this evening. I am now pleased to introduce Dr. Robert Mann, Professor of Physics at the University of Waterloo and the President of the Canadian Association of Physicists, to introduce Dr. Townes. Thank you all, and I wish you a very successful Congress.
Bienvenue, mesdames et messieurs, à la Congrès de l'ACP de 2010. Welcome, ladies and gentlemen, to the 2010 CAP Congress. It's a delight to see this audience so full and to have what, to my knowledge, is the largest CAP Congress in our history, in which we have not shared the meeting with any other group. And it is your participation here that is making this meeting a great success. I was at a conference a little more than a week ago in Taiwan, and there was a discussion amongst us about physics and what it's like to be a physicist. And one of the people there once said they were asked by someone from the public, what exactly is it that you physicists do anyway? What good is it? And she was able to answer in one word, lasers. And the person instantly understood the importance of the discipline. And as we have just heard, they are used in barcode scanners, they're used in pointers, they're used to cut metal, they're used in surgery, they're used in scanning. Where would we be without this development that occurred 60 years ago when Theodore Maiman made the first optical laser? But that invention, as we know, had its roots in the work of Charles Townes, our speaker tonight, who in the 1950s had the idea that he could indeed create what was theorized at the time, that one could in fact take a group of atoms and construct a population inversion so as to stimulate radiation in a coherent fashion. It was in the microwave regime, and so it was called a maser. But shortly afterward, Charles and Arthur Shallow, who I learned is Charles' brother-in-law, or became Charles' brother-in-law, wrote a theoretical paper which suggested it should be possible to do this in the optical regime. Nowadays, we take these devices for granted, but there are a number in this audience who can think back and remember a time when lasers were non-existent or perhaps out of reach of the average person, and now they can be purchased for pennies, basically, or maybe a few dollars. Charles Towns was born in the United States in a place called Greenville, South Carolina, and I learned when he attended high school he did not take a single science course. He did take mathematics. He felt he would learn science better at university, and I am pleased to say that when he took university physics, he thought right away, that's for me. And I think all of us in this audience are glad that he had this change of heart. He is a descendant of a family that is interested in law. His grandfather and his father were both lawyers, as is one of his brothers. He comes from a family of 6. He has a brother who's a biologist, as I said, and his sisters are interested in music and librarianship and English teaching, so it's quite an interesting family. Charles began work with Bell Labs. He went to Furman University, followed this up with a master's at Duke University in the United States, and then went to the California Institute of Technology for his doctorate. He was the provost at MIT in the 1960s, and then he eventually went to Berkeley in 1967, where he remains a professor still at the age of 95 next month. He just graduated his 80th doctoral student. He has been an advisor to 3 American presidents, Eisenhower, Kennedy, and Johnson, on their scientific advisory committees. He has sat on advisory boards for General Motors and PerkinElmer, and currently on the Templeton Advisory Board for the John Templeton Foundation, which is where I first had the pleasure of meeting him 2 years ago. I would like you all to give with me a warm welcome to Charles Towns, who will tell us about 50 years of laser physics. Charles.
Thank you. Well, I'm very, very pleased to be here, especially to honor Gerhard Herzberg, who's such an important figure. He's contributed a great deal to my own work, to the laser and the laser, as well as spectroscopy, and we're all thankful for his great work. And I'm very pleased to be here to honor him, and pleased to be with you. Now, I've been asked to talk. Actually, I was asked to give 2 talks, or at least on 2 different subjects. One will be some of the origins of the laser, how the laser came about, a kind of historical thing. The other is in my present work, where I use lasers to do astronomy, measure the sizes and shapes and behavior of stars. So I will give 2 relatively short talks. I hope I can get through them both in time for you. Now, the laser, of course, is a kind of a new idea, a new discovery. And how do new ideas and new discoveries come about? That's an important thing, and I want you to think about that. New developments come about in a variety of ways, but some of the things that are important are the interaction between different fields. Different fields of science and technology interact, and that produces new ideas. Interaction between science and engineering, for example, is important. Now, secondly, the interaction between people. People talk to each other, and they, oh, hey, I wonder, that's interesting, and so on. And people talk to each other and trade ideas, and you get new ideas that way in part. Another thing is we need open-mindedness. You'll find in my story some people are very close-minded, even fantastically good scientists, close-minded, they get locked into certain positions. We've got to be open-minded and think about possible changes and where could we misconceive things and so on. Now, also, of course, essentially all new scientific discoveries come about from very careful, substantial work. Sometimes those discoveries are accidental and not the things that people are looking for, but by looking carefully, something else turns up. Sometimes they're the result of very hard, intensive work directed in that direction, and that's the case of the laser. But I was at Bell Telephone Laboratories when the transistor was invented. And Walter Bratton been carefully measuring the properties of copper oxide on copper wires. And he found something he didn't understand, how it was behaving. He didn't understand it, but he thought about it. Well, he couldn't figure it out. And he went to John Bardeen, who was a theorist, said, what's going on here? And John thought about it, said, hey, you've got amplification. You've got amplification. Discovered completely accidentally the transistor. Think how important it's been. In addition, one of my former students, I had him do his thesis looking for hydrogen, atomic hydrogen in outer space. I thought, well, maybe there's hydrogen floating around out there, all between the stars and so on. We should look for it. And we had a special maser amplifier. It was very sensitive. We could look for it. And he looked. He didn't find it, but he managed to do a good thesis. Then he went on to Bell Telephone Laboratories, and he continued to look. And there with Arno Penzias, who was a former student of mine, and Bob Wilson, they continued to look, and they didn't see hydrogen, but they found a signal up there. They had a very sensitive amplifier, they were looking carefully, they found signals, and the signal come from all directions. What was it? It represented the Big Bang, the beginning of the universe. So they discovered the beginnings of the universe accidentally, but by very careful, thoughtful measurements. They saw a little something that, they figured out, now what in the world is that? And so they figured it out. That's the beginning of the universe. So that's how things happen accidentally, but some as a result of careful, systematic work. Now, in my own history, I always wanted to do physics. At least after I went to college, I decided physics was really what I wanted. 1939, I got a job at Bell Laboratories. Jobs were very scarce then. I wanted to go to university, but I got a job at Bell Laboratories, which was good. I did physics for a little while, but the war was coming on. And so I was assigned to build a radar system. Oh dear, I had to do engineering. I had to leave physics and do engineering, and I was assigned a job of trying to build a radar system, and the radar system at shorter wavelengths than they'd had before, wavelength of about a centimeter, half an inch. And so we designed and worked on this radar. As we'd worked on quite a bit and built quite a bit, we discovered that wavelength was absorbed by water vapor in the atmosphere. Oh dear, that ruined the whole radar system because that wavelength was absorbed by water vapor. Well, I continued to work on radar of other types and so on during the war, which I had to do, but after the war they let me get back to physics, and I said, I want to examine. I didn't realize you could, these molecular lines in the microwave region, and I had a lot of microwave expertise as a result of my radar work. I wanted to try to examine the spectra of molecules with microwaves, which is a completely new field. So I did that. You could measure the water vapor line, its shape, and all of that, because you get very high resolution with microwave amplifiers. And a lot of molecular work. And I used Herzberg's books, which are very important to me, in interpreting these spectral lines and so on. And that became a very important field, and exciting enough that I was offered a job at Columbia University, and I went to university then, at Columbia University, and I continued to work. And I wanted to get down to shorter wavelengths. Now, the oscillators of that day could be made down to about, a few millimeters wavelength you could produce, but nothing shorter. Engineers worked hard on it, and I thought about it and worked hard. I had some of my students try various things. Nothing worked. Finally, I was appointed chairman of a national committee to try to see how one could get an oscillator at shorter wavelengths. I wanted to get on down into the infrared, down below a millimeter anyhow, in the infrared region. But we just get, anyway, anything would get substantially shorter. And we had this national committee of very famous scientists and engineers. We traveled all around, visited anybody that had any ideas. And after a year, no ideas had turned up. We had decided, well, we'll have our last meeting, so we just can't find anything. We met in Washington. I waked up early in the morning worrying about it. And it was a bright, nice sunny morning, as it's been here. I went out and sat on a park bench. But why hadn't we got any ideas? Gee, now I've tried this, and we've tried this, and thought about this. And of course, molecules and atoms can produce high frequencies, but you can't get them to amplify. Well, now wait a minute now. If you have more of them, they always absorb. They just, heat them up, and you can get some energy, but you can't get very much. You can't get a good oscillator. But wait a minute. In the upper level, if you have an excited molecule, it can drop down and give energy. The lower level is absorbed, and the normal temperatures are more in the lower level than the upper level, so molecules always absorb. But hey, if we can get more in the upper level, then they can amplify. Stimulated emission was known. Now, that idea had been known for some time. It was suggested by Einstein. And all the ideas on which the laser is based came along as early as about 1920. It was known, but the laser wasn't invented until, 35 years later, roughly. Why? Well, you see, people were just blocked, and we didn't think in the right direction. I said, well, I pulled out a piece of paper and a pen, and I wrote down an equation to see, now, can I possibly get enough molecules in the upper state to get amplification? I wrote down the notes and the formulation and so on. I said, hey, looks like probably will work. I didn't tell the committee about it because we were writing our last report, and it was a negative report, and this was kind of iffy anyhow, so I didn't tell the committee about it. We wrote our report, but we hadn't found anything, and I went home, and I looked at it some more and wrote it all out in a notebook. And of course wrote it down as a patent because I thought this was a useful idea. And then I decided to find a student, and I got a student, Jim Gordon, to work on it. Jim Gordon had, and I felt, well, I would use molecular beams. Now, why molecular beams? Well, there were two professors in our department, very famous, I. Robbie and Polycarp Cush, who both had Nobel Prizes, and they had worked on molecular beams, and I understood molecular beams, they could separate the molecules into excited states and lower states with molecular beams. And so I would just do that. And I got this student to work on it, and he'd been working a couple of years. And Robbie and Cush was then chairman of the department. Robbie had been previous chairman of the department. They both had got Nobel Prizes. They came into my lab and said, look, Charlie, that's not going to work. We know it's not going to work. You know it's not going to work. You've got to stop. You're wasting the department's money. You've got to stop. Well, fortunately, by then I had an associate professorship. The associate professor can't be fired just for being stupid. He can be fired if he does something morally wrong, but not for just being stupid. And they couldn't fire me. So I said, no, I think it has a reasonable chance of working. I'm going to continue. Well, they marched out of my laboratory angrily. About 3 months later, Jim Gordon, the student, came into my classroom where I was lecturing. He came, hey, it's working. So the whole class, dashed out and went into the laboratory to see this thing. It was working. Yes, we had an oscillator based on molecules, ammonia molecules. Beam of molar molecules are separated more in the higher state than the lower state, and they went into the cavity. And the oscillations, the waves moved back and forth in that cavity and got energy from the molecules. And it was working. Wow. Well, my students and I had some lunch together, figure out what do we call this. We decided to call it the MASER, microwave amplification by stimulated emission of radiation. Stimulate the molecules to radiate, microwave amplification by stimulated emission of radiation, MASER. So that was the name. Well, now, a lot of people had come in my lab and looked at what we were doing and said, oh, yeah, well, that's an interesting idea, but nobody competed. Wasn't anybody else working on it, excepting two Russians, And I wasn't in contact with them. They didn't know what I was doing. I didn't know what they were doing until after we published. After we published the results showing that this thing was working, then they got in touch with me. And I know Bassoff and Prokhorov, and they got the Nobel Prize with me because while they didn't build one, they had a similar idea and they were trying to build one. But nobody else was interested. Once it got working, then everybody was interested. Everybody jumped into the field, and industry hired all the students who had been working in this kind of field. They started hiring those people so they could work with masons and so on. And the field began to develop. Well, I took a sabbatical leave shortly after that, and I went first to Paris. In Paris, I ran into some friends who were working with electron spins in solids, and they found that they could put the electron spins up, they'd stay up for a long time before they fell back down again. Oh, wait a minute, we can make a maser out of that. Electron spins, and put it in spins in the magnetic field. We can tune it, so we've got a tunable maser. Oh boy. That was an idea. Now, we wrote a little paper about it, and Nico Bloomberg at Harvard read it, and he said he's been working with electron spins. He'd had 3 levels, and so, oh yeah, well, he can excite from here up to there and then have it fall down to there and amplify. And so he added to the idea. I went on to Tokyo on my sabbatical. There I met a biologist, Francis Ryan, who had been studying the variations in the numbers of bacteria. And he'd studied a paper where the bacteria, the formulation had the bacteria dying or splitting and multiplying. And the mathematics was trying to look at the statistics of how much the numbers of bacteria would vary. I said, hey, wait a minute, that's just what I want in order to understand the amplification with masers, to find out what the noise is, what are the fluctuations. Because the molecules can fall down and give up energy, they can absorb energy, or they can be stimulated to give energy. And that's something that didn't happen biologically, but that put an additional term in the equation. And so Francis Ryan and I looked at it, and we worked out the equations, and that allowed me to work out the fluctuations in the maser and show that the maser was the most sensitive amplifier we'd ever had, get down to the ultimate limit of sensitivity. And it was a maser that found the Big Bang and so on, and masers have been the interesting amplifiers, and that was another field that grew and grew. And so masers are growing very fast. And I got back to the United States. I kept working on it for a while, but then so many people in the field, I feel, well, they don't need me. Anyhow, I want to get down to shorter wavelengths. That was my primary aim, to get on down to shorter wavelengths, at least down in the infrared. And how do I do that? Let's see. I built it first at microwaves because I had all the microwave equipment. I thought, well, I'll see if it works in the microwave region first. But what I really wanted was shorter waves. So I sat down and wrote down notes. Let's see, how shorter wavelengths can make this work? And nobody thought it could get down to light waves. Nobody was interested. Nobody talked about it. I wrote down the equation. Hey, looks like I can get right on down to light waves. With the same idea, get right on down to light waves. I wrote this down. I knew by then it was such a popular field, if I said anything about it, everybody would jump into it and try to beat me at it. And actually, I was consulting with Bell Telephone Laboratories. My brother-in-law, Art Sharlow, who graduated from here, he'd worked as a PhD with me, worked as a postdoc with me, and married my kid sister. I was glad about that. And he was working at Bell Telephone Laboratories, and I talked with him about it, said, I've been very interested in that. Could we work together? And I said, sure. So we worked together on it, and we decided, well, we probably ought to give the patent to Bell Telephone Laboratories. And I told him to take this idea to Bell Telephone Laboratories lawyers and have them patent it. For Bell Laboratories, we'll give them the patent. He called me up next week and said, well, Bell Labs lawyers say they don't want to patent it because they say light's never been used for communication, and they don't think a bit of any use for Bell system. And I said, oh, well, they just don't understand. And he said the lawyers told us, well, you can just take the patent yourself. Well, tell them just because the lawyers don't understand, we shouldn't rob Bell Laboratories. You go tell them, yes, it can be used for communication. So we called them back and said, well, the lawyers say if we can show how it can be used for communication, then they'll patent it for Bell Labs. So we did. We wrote a patent called Optical Masers and Communication, and that was the patent. Now, We still didn't talk with anybody else about it because I knew if it's ever mentioned, a lot of people would jump into the field. I knew if I started working on it, I couldn't have a couple of years to work on it and make one work because other people would come in that would compete. In addition to that, I just accepted a job to go down to Washington for a couple of years to try to advise the government. So we decided we better keep quiet about it until we write a theoretical paper showing how it could be done, and we'll publish that, and then everybody will jump into the field. And that's what we did. We wrote a theoretical paper. We called it optical maser. A little later, then everybody started calling it a laser, light amplification by stimulated emission of radiation. From masers to lasers, they're the same thing, they're just different wavelengths. And of course, if you get in the infrared, you might call it an eraser, but eraser already means something else. So infrared masers are lasers. Anything below 1 millimeter makes it a laser. Anything above 1 millimeter, that makes it a maser. Well, so once we published this paper, then everybody jumped into it, and the industry had hired a lot of students in the field because of the maser. And so all the first lasers were made in industry. The very first one was made by Ted Maiman at Hughes, and he made the Ruby laser. He used a pulse. Now, I hadn't thought about using high-intensity pulses, but he had, and he used a pulse, and then he made it, and of course everybody started reproducing it and making others. And then one of my students, Ollie Javan, at Bell Telephone Laboratories, built the next laser, a continuous laser, the first continuous laser, the helium neon system. And Ollie had worked on this for some time. He had left my laboratory to go to Bell Laboratories and started working on that. And then all the first lasers, I say, were produced in industry because industry had all the intelligent students in the field, many of the students and intelligent students in the field they had hired. So there it was. And of course it's grown and grown and grown. And an enormous big field now. I could foresee some of the things it was going to be useful for. I knew it was going to be very useful, especially in science, that I could see, and that's where I wanted to use it, the science. But some of the things I completely didn't see, for example, all the medical and biological applications, it didn't occur to me. Burning and welding and cutting and so on, and accurate measurements, that I could foresee, even though the Bell Laboratories lawyers didn't see communications. That seemed obvious too. So now, you see, the community has made it grow. And the field grows as a result of interaction. You notice the interactions I had with various people, getting ideas and trading ideas, and I interacted with Art Charlow. Now let me show you a few transparencies about these things. And that will be the story so far as the origin of the laser is concerned that I'm going to tell. Here were the notes in my notebook, my first notes. There, you see, there is a molecular beam. Hey, that's a laser. A beam of molecules comes out here, comes through a slit, a small hole in a slit, comes through here, and then electric fields separate the molecules. The ones in the ground state are pulled out, the ones in the excited state go on. They go into a cavity, and then in this cavity, the waves bounce back and forth in the cavity. They're held into the cavity, and they get energy from the molecules. The molecules pass on out, and so then we get the oscillation. That was the idea. Next, let me show you the first maser. This was done by Jim Gordon, who's right here as a student. There I am. And this is the first maser. And you see, the molecules came from here. They go through this, there's an electric field here, and they come into a cavity and oscillate. These are just vacuum pumps to pump this out. This was a cavity. This was a plate on here to make it a cavity, to make there's a vacuum in there so the molecules could travel as they wished. Now, here's the idea. Now, I would have to say that it was Art Charlow who added the idea for a new kind of cavity for the optical waves. I had in mind a cavity in which the waves would just all bounce around, and that's the way the microwaves work. I thought of the same thing for the light waves, but he said, no, wait a minute now. We want a single mode, a single kind of oscillation, and we can do it by having two parallel mirrors here, and the light goes back and forth, straight back and forth, between the two parallel mirrors being amplified. These are just representing molecules. Here's molecules as they emit in all directions. But once you have a wave coming along, it stimulates the molecules to emit in the same direction as the initiating wave. And so as the waves build up, it makes more and more and makes a very intense oscillation then inside of this cavity. So now, why did Art have that idea? Well, he'd been working with a Fabry-Perot for spectroscopy. Two parallel plates of the Fabry-Perot does very high resolution spectroscopy. He'd been working with that. That's why he had that. But he added that idea, which was a very important one. So there's the history of the initiation of the laser. And of course, again, let me emphasize that an enormous number of people have since then contributed, and that's very important in the growth of science and technology. It's grown and grown and grown. Some things I could imagine, some things I didn't imagine, but I'm just delighted to see all the different contributions and what has happened. Now I'm going to talk about the science I'm presently doing. As I say, I've been asked to give 2 talks, which is really too much for you maybe, but I hope I'll get through in not too long a time. Science I've been doing is measuring stars, studying stars, their shapes, their sizes, their change in sizes, watching them blow off material and so on. That's called interferometry. Interferometry was first done in the early 20s by Michelson. He was the first person to measure the size of a star. He didn't measure it very accurately, but he was the first, nevertheless, to measure the size of a star with interferometry. He had 2 mirrors on either side of the 100-inch telescope down in Mount Wilson in Southern California. 2 mirrors. Light would come from the star, these 2 mirrors, and he joined it and it interfered. Well, a lot of other people tried that, but they tried it with separate telescopes because they wanted to put them further apart. The separate telescopes would shake with respect to each other, shake so much, shake a fraction of the wavelength of light, and that would destroy the interference. Light waves wouldn't interfere if they were shaking and moving. Well, lasers have changed that because lasers can stabilize or keep measuring just how the mirrors are and keep them stable. And lasers then have made interferometry, again, a very popular field. People tried it after Michelson with 2 separate telescopes. They could never make it work. Once lasers came along, we can have 2 separate telescopes. We can move them as far apart as we like and keep them stable enough that we can do interferometry so we can resolve very small stars, smaller and smaller stars. Michelson, when he resolved the star, he resolved one of the biggest stars in the sky, Betelgeuse it solved. It's one of those, a very bright star. And that was the only one whose size was roughly measured. He measured fairly roughly, but still he measured it. Nowadays, we're measuring a lot of stellar sizes, and it's a very important and growing field. I'm doing it in a somewhat special way, however. And I have 3 telescopes, so we can get interference between 3 pairs of 2 each. The other 3 telescopes, which are down on Mount Wilson, and in this particular case, they're placed 4 meters and 8 meters and 12 meters apart. We can combine beams from any 2 of them, and you see they're in trailers, so I can move them around and make wider and wider separation, and that gives me a good deal of flexibility. But now, in addition, I have a special kind of detection, heterodyne detection. Lasers have made heterodyne detection in the optical and infrared region possible. I'm working in the infrared with wavelengths about 10 microns. It's about 20 times the wavelength of ordinary light in the infrared. And here are sort of diagrams of 2 telescopes. And this is a diagram of the heterodyne detection. We have a laser, which is this local oscillator, so-called. It shines light into a detector, the solid-state detector, which detects the light. But we have light from the star coming from this telescope going into that detector too. So we mix the light from the star with the local oscillator, and the 2 beat together, and you get a difference frequency. Now that's the way that radio waves are almost always detected, heterodyne detection. That's been used in the radio region the microwave region for a long, long time. Only now can we do it in optical and infrared because of the local oscillators that we have. So we mix, mix the laser light, this is a CO2 laser, with the light from the star. We got a beat frequency, and then the beat frequency comes out and we amplify it. We got a beat frequency from the stellar signal in this telescope. We amplify it. We bring the two together, let them beat together, and then we get a fringe. There's the beat. And now, the beat occurs at various frequencies. If the stars are exactly fixed in position, and the light comes through the atmosphere without changing the path length, without the atmosphere density changes, then the beat frequency is a very pure frequency. Here it is. That's a signal of a signal from a star beating two stars coming into two telescopes, and they made the beat together, and there's a signal. And the fact that they beat together means the stars must be small, not resolved by the interference between the two telescopes. Now, the interference, if we bring the light from a star, from a point source here, together, as the point source moves just a little bit, the waves will add or subtract. Because the distance to the star changes as the star moves. Waves will add or subtract. As add or subtract, that makes an oscillation. That oscillation depends on the speed of rotation of the Earth or the motion of the star, you might say, overhead. And this oscillation is fixed at about 100 hertz. As a sign. But now, ordinarily, the atmosphere is fluctuating in density. There's a fluctuation in density. The distance from the star to this telescope, the distance from the star to this telescope, for the light wave, the distance of the light wave changes. As the air increases density, that makes the path length longer. And so the waves change as they come in, and that makes the beat frequency between the two not very fixed. And there it is broadened out. It's broadened out due to fluctuations in the atmosphere, broadened out about plus or minus 10 hertz, you see. And that's about the frequency at which the atmosphere changes. The flickering of the atmosphere changes about a few times per second. And there is a beat frequency between the two stars oscillating where the atmosphere is varying. Here the atmosphere is superbly constant. That's very rare to get at anything that good. So that's the signal. Now, if you move the telescopes further and further apart, then as the star moves, as a point source moves across the sky, the interference goes up and down, faster and faster. Goes faster and faster and faster as you move the telescopes further apart. So as you move them very far apart, the star gets resolved, and it's just averaged out, and you don't see any signal. Because you're seeing this part of the star has a positive signal, this part of the star has no signal, and it just averages out. If the star is bigger than the up and down of the interference. So that's the way we resolve the stars and decide just how big they really are. Now here is, for example, the power in the fringes of Betelgeuse, a star that Michelson resolved first. And this is the spatial frequency. This is the number of times on the sky the signal goes up and down per radian. Now, a radian is about 60 degrees, and it goes, at this point, it goes up 1,000,000 times every 60 degrees. In other words, about 16,000 times per arc second. So this, and here is higher and higher resolution. This goes 2 million times per radian. This is 3 million times per radian. Now the visibility of the star, visibility would be 1 if the star were a point source. The stars resolved even really when our telescope's about as close together as we can bring them. That is not really the star, but the dust around the star. Betelgeuse has a shell of dust around it, about a couple radii away from the star. And the dust gives a good deal of the infrared radiation. It gives, you see, about 4/10 of the infrared radiation here, 3 or 4/10 of the infrared radiation. So the dust is all resolved. Here, we resolve more and more dust closer and closer to the star, and we keep resolving it. Now, we begin to resolve the star, though, and here's a picture of where the star itself is resolved. This is the visibility, or the up and down the star as we get down higher and higher frequencies. This is 4 million times per radian. And the other star is essentially resolved. So this is the resolution of the star. By looking at how fast this curve drops, we can decide what the size of the star is. So, and I have measured the star of Betelgeuse. I've measured its size to about 1% precision. And we have found over the last 15 years, it's been shrinking in size. There's the size. Now this is 55 thousandths of an arc second is the size. And this was back about 16 years ago now, about 56 arc seconds, maybe, and then it slowly decreased. And here's the reason, this is over 15 years. This is over 15 years, it decreased about 15%. We find now in more recent measurements it stopped decreasing and started going up a little bit. Why? That's new. Nobody knew that Betelgeuse was doing that. Some stars change a lot, and that's been known, but a star like Betelgeuse, people didn't know it did that. We found it. Why? We don't know, except it's not surprising that it could change. It's a big old star, not like our sun. Fortunately, our sun is very, very constant. It's a big old star, and here we found it's not constant. Well, that's a new discovery. And it hit the newspapers. But now there are stars that change regularly with time, and that's been known for quite a while. Mira, for example, was discovered by the Arabs. Mira gets bright enough to see at some point, and then it fades out and you can't see it. The Arabs discovered that. And that kind of star is now called a Mira. And it oscillates in intensity about every year. It gets brighter and weaker on a year's time scale. And we have, for the first time, measured its size and its size change. And there is the change in size over several years. This is about half of 1 year, this is half of another year, half of another year. And you see, this is the size. It changes from about 55 down to 47, and it even gets lower. The size of the star changes, we think, about 30% in all. And it's brightest at about here before it gets its biggest. Why? Because as it gets bigger and bigger, it cools off. It's bright, as it gets bigger, it's still fairly hot, it's pretty bright here, but then it cools off, it gets weaker here. So the star gets brighter and weaker, and the Arabs noticed that. They didn't know the size, of course. Now we've measured the size, measured the phase of when it's biggest. Now this star, as in many old stars, also has gas around it, as well as dust. And we have a very narrow bandwidth in our detection. Because we're using heterodyne detection, we use a very narrow bandwidth, narrower than anybody else uses. And so we can separate the spectral lines of the gas around the star from the continuum radiation of the star itself. Most interferometry doesn't do that. They have a wider bandwidth. When they look at an old star with gas around it, they're seeing some kind of combination of the gas and the dust and the star, and they don't know how to separate them. We can separate them because they have a very narrow bandwidth. And here is a picture of when we are off of a spectral line. That's the star. We're on a spectral line. This is how the visibility decreases. Visibility decreases much faster when we're on the line. That means the gas is bigger than around the star. And from this, we can decide the water vapor starts at about 30% of the size of the star away from it. 30% of the diameter of the star away is where the water vapor occurs. And we can measure it, and there it is. And you see the two separate lines. Now, if you don't have a narrow bandwidth, you get some combination of that. You don't know which you're measuring. Now, there are many stars that have not only water vapor and other gases around them, but have a lot of dust. And some of them are so covered with dust you don't see anything else. For example, here's a star here. There's a star here. This star is W Hydra, and this is the visibility curve as a function of resolution. It just steadily decreases, and this is resulting intensity as a function of position. This is 200 milliarcseconds. This is 1/5 of an arcsecond, plus 1/5 of an arcsecond, minus 1/5 of an arcsecond. This is the intensity of a dust shell around the star. This is the star itself. The star is much smaller than a dust shell, but this is the infrared intensity. Goes like this, you see, and the star produces something right here in the middle, but the star is unresolved, really. The dust shell is this, so that shows the intensity of the dust around the star. Now, many stars have a very sort of fairly large, constant dust shell around them. These are old stars especially, and we don't see the stars. We mainly see the dust. But some of them vary a lot. And now here, and they blow off dust shells rather than having a simple distribution of dust around them. This is NML tau in the constellation Taurus. This is a visibility curve, 1992, 1993. You see it has wiggles in it. And if you figure out what the intensity of the dust is, intensity of the dust is a function of distance from the star. 1992 is a solid line. You see it has 3 bumps in it. 3 bumps in it, corresponding to these bumps up here. 3 different dust shells. The star blew off dust at different times and then stopped. So the different dust shells. And now 1 year later, these shells have seemed to move, you see. See, these are different. The 2 curves are different years. These shells have moved. We can tell how fast they're moving. So from that, we can say how fast the dust is moving out from the star. Now, as a matter of fact, it also allows us to tell the distance to the star. Why? We can tell how fast it's moving in angle, and people can measure with Doppler effects. They can measure the velocity of the gas moving away from the star. So we know the velocity, we know the angular change per year and the velocity. We can decide how far away it is. So we can measure the distance to the star really quite precisely. The best way of measuring the distance to a star, actually. Well, now, finally, I'm going to show you another star that's a very unusual star. This is the brightest infrared star that we know. It's called IRC plus 10216. You see, it was discovered only recently because people didn't discover stars in infrared until fairly recently. It's the brightest infrared star in the sky. You can't see it with visible light at all. And these represent the curves of visibility. But also, we can determine the asymmetry in the star because we have 3 telescopes. We can measure the visibility in this direction along this baseline, this baseline, this baseline, measure the asymmetry. And here's how the dust is distributed. This is intensity. This is where the star is. Most of the dust is on this side, at least the peak there, but some is on this side. That's the distribution. These 2 curves represent 2 different years. It changed with time. So it's changing with time, blown off material very asymmetrically. Why? We don't know. Maybe there's a pair of stars there or something, but we can't see it in the visible, and we don't know. But it is the brightest infrared star that is known. Now, we will, of course, continue to watch these things with time because they change, and we measure the shapes of stars. We find some stars are a little asymmetric. Betelgeuse, for example, we found over about 1 year's period, it seemed asymmetric. We think by our measurements, however, this was due to a very bright spot on one side of the star. It developed a very bright spot. Our sun, of course, has sunspots. They are small compared to the total intensity of the sun. But this is a bright spot that had about 15% of the total intensity of the star, the big bright spot. And it made it look asymmetric, as well as a little change in size. Then it went away in about a year's time and hasn't done that since. It's been changing. The overall star has been changing in size, but it's round. So you see, these stars are doing a lot of things. Many of them are very active. Our sun, in many ways, fortunately, is very, very constant. It has a lot of little variations on the surface, but on average, it's very, very constant, thank goodness. Otherwise, we would boil or we would freeze. But these other stars, particularly older stars, change a lot with time, and change over relatively short periods of time, too. They're very active in doing things. So we want to study them, continue to study them, watch them change, figure out what they're doing, and as we study more and more and find out more and more, we will understand these stars more. Well, now that completes my 2 talks. I want to illustrate, you see, this is just a place where lasers have become important. Opened up a field again that really was rather poor and difficult. Now we can do interferometry at very high angular resolution, very high spectral resolution. You can make rather precise measurements. As I say, I measure the size of stars are somewhat better than 1%. And a lot of people are doing it. The field has grown fast. There's a lot of interferometry now on stars. Lasers have opened up many, many different fields, and I'm just very thankful for that. And thankful for all the contributions so many different people have made. Now, I want to emphasize again, we want to interact with people. That's the way new ideas grow. We want fields to interact. We want to be open-minded, of course, very thoughtful. We don't want to just imagine things and say, oh, well, maybe it's this way, maybe it's that way. We think hard about things. Nevertheless, be open-minded. Let's don't be closed-minded. Now, as an illustration of that, I'll tell you just a few more little stories about the laser and the maser. After we had the maser going, it had a very, very pure frequency, and I was very pleased about that. And I was visiting Niels Bohr in Denmark, whose son I knew, Bohr, and both Niels Bohr and Bohr have Nobel Prizes in physics. His son was more or less my age, and I knew him. And I was visiting Niels Bohr, and we were walking along the street, and Niels Bohr asked me what I was doing. I told him, well, we just had this new kind of oscillator with molecules doing this, and they had a very, very pure frequency. He looked at me and said, oh, no, that's not right. That can't be right. No, can't do that. I said, yes, no, we have it. It's working. Oh, no, that's not right. I said, no. Well, he just wouldn't listen anymore. Now, I'm pretty sure he was thinking about the uncertainty principle. See, the molecules, it went in my beam a certain finite time, and you can't measure the frequency of a given molecule in a finite time with more than a precision which is 1 over the time. I imagine that's what he was thinking of, but he just didn't want to talk with me anymore. He thought I was so crazy. Now, I also ran another famous physicist, von Neumann, John von Neumann, mathematical physicist, and with cocktail party. He said, you know, what are you doing? I told him we had this oscillator, very pure. Oh, no, he said, no, that can't be right. You misunderstand. No. Oh, yeah, no, I said, no, that can't be right. Well, he went off, and got another cocktail. And about 15 minutes later, he came back with a new cocktail and said, hey, you're right. Please tell me more about it. Now, you see, engineers have no problem with getting a pure frequency out of an oscillator. The electrons in an electron tube don't stay there very long and so on. They have no problem. They know that you average out a number of particles and you can get very high precision. But Bohr and von Neumann, they were just thinking in the directions that quantum mechanics told them, and they weren't open-minded. That's something we must all watch out for. I would say the same thing about Professor Rabi and Kush. They both Nobel laureates. They wanted me to stop. They knew what I was doing wasn't going to work. Well, it did work. Well, actually, after it worked, sometime after it worked, they came around and congratulated me. Even though they told me to stop and that I didn't know what I was doing. And I was working in their field using molecular beams, you see. we've got to explore. We've got to be open-minded. And, yeah, listen to other people. Listen to their ideas. Trade ideas with other people. Get ideas from them. Let them get ideas from you. The growth of the MESA and the laser has been very, very dependent on the trading of ideas and the contributions of many, many different people. And that's what we need. So science, engineering, they're just wonderful. Just great fun, great fun. I hope all of you will enjoy it. Thank you.
I'm going to present this later, but first we'll take questions.
Sure. I'll be glad to take questions.
You could stand a little bit over there. Well, thank you. Thank you very much, Charles, for that stimulating presentation. And I understand that Charles will be happy to entertain questions from the audience, so please raise your hand and speak clearly. Oh, are there microphones available? Okay, then please make use of the microphone.
Hello, Professor Towns. Very inspiring presentation. I noticed that even though the main message of your talk is about talking with everyone, that there came a moment in your research where you felt you had to keep something to yourself. And I wonder if you could comment on that to guide researchers who might be wrestling with the same thing. Should we not talk about everything all the time? Or is there some point at which you need to keep things a secret for a little while?
Yeah, that's a good question. Why should we keep a secret? In fact, trading ideas is very important. Why keep a secret? Well, of course, scientists not only trade ideas and help each other, but they also compete. And when I was building the MESA, as I pointed out, nobody was competing. So we could work at it, and I could have one student working at it and doing his thesis, and it took 2.5 years to do it, and that was okay. But once the field becomes very exciting and important, have an exciting idea and other people think it's exciting, then they compete. So you want to finish it first and get it published first. So, well, you had the idea first, you want to publish before somebody else comes in and publishes before you do. So there is competition. We want to publish first and show that we were the ones who had the idea and got it started. So that was it, you see. I knew that when the laser came along, I knew if I said anything about it, a lot of people would jump into the field, particularly industry and so on. They could work much more intensively than I could. I was down in Washington, consulting down in Washington. I had students who could work on trying to build a laser, which they did, but I was going back and forth. I didn't have any time for it. So I was sure somebody else could build one before we could, and they would beat us to it. So they would have invented a laser. Well, no, I wanted to show that I had the idea at least. So that's why we published the idea, you see. We published the idea without actually doing it. Then somebody else did it first, namely Ted Mayman. So he actually made the first laser. And that's the reason I did that. Now, it's not, I think that's, one needs to watch out in science. We don't want to hide things from other people. We want to trade ideas, because that's how science grows. And I did trade ideas, but I just wanted to publish the theoretical idea first.
Steve.
Do you know why Rabi thought it was not going to work? What was his idea?
What was the question?
Why did Rabi believe it would not work?
I don't know why he didn't believe it worked. He didn't explain it to me. I think he felt, well, gee, I was doing things that they knew all about, namely molecular beams, and I probably wouldn't know what to do. And they didn't work out the equations or think about it very carefully. I think he just had the instinct, oh, it's probably not going to work. But I don't know, he never told me.
It's not just because the inversion is not thermal. He expected it to be thermal?
No, surely he understood the quantum mechanics. Surely he understood the quantum mechanics. I think he just felt the whole thing wasn't going to work, wasn't practical. Wasn't practical, you see. Well, he surely understood the quantum. In fact, the quantum mechanics was understood by most physicists for many years, from about 1920 till when I built the first MESA in 1954. For 34 years, roughly, The ideas were well known, but not applied because people didn't think in the right directions. It was that combination of engineering and quantum mechanics that helped me.
Sir, following on the answer to the first question. Okay, following on the answer to the first question, you shared the Nobel with 2 Russians. I assume you prefer to have shared it with Mr. Gordon and Mr. Shallow. You're nodding your head. Okay, so but you said the Russians never actually built a laser, but they published a theoretical article about it.
Yes.
So perhaps you could give us more details, and perhaps you could tell us why you would rather you feel that probably the Russians deserved it less than your associates.
Well, of course, I'm not the one who decides who gets a Nobel Prize. It's a committee out there. It makes a decision. Decisions are not easy. There's a lot of good work and decide who should get what. It's difficult. And the Russians, yeah, they didn't build one, but they did have the idea. And Art Shallow had an important idea. And in fact, you may be amused, when we got a call from Sweden, it was called to my house, and I was away at a meeting at the time, so they talked to my wife, told them I'd got a Nobel Prize, and the Russians had. And she said, "Oh, no, not the Russians." And then I was, when daylight came to where I was called about, and the newspaper people called, "Why did your wife say that?" What could I say? I said, "Well, I suppose she probably wanted all the money herself." But actually, I think she was thinking of Art Shallow, and I think Art Shallow might have gotten it with me, but the prize can't be given to more than 3 people at once. And Nobel people are very eager to recognize people all over the world, not just too many people in the United States or any one country here. And so they like to spread it around some. And of course, Art Shallow later got a Nobel Prize for further work using lasers. Further spectroscopic work, he later got a Nobel Prize, and he certainly deserved one.
What was your reaction when astronomers discovered masers in space?
What's that again?
What was your reaction when masers were discovered in space? I mean, you in space, out there in the universe, you have masers, right? You have.
He's asking what was the reaction when masers were discovered out in space.
Oh, yes. Yeah, I was very pleased that masers were discovered in outer space. In fact, there are not only masers out there, and there are many masers, but there's some lasers in outer space. And I would point out, well, that's another way they could have been discovered. If we'd been looking in the microwave region carefully, we would have found these water masers. There's lots of water masers out there producing very intense energy at the water frequency. If astronomers had looked carefully in the radio region, they would have found them and said, "What world is that?" And then they would have figured them out. Oh, wait, they amplify, oh yes. And we would have discovered masers that way probably. But we didn't because they weren't looking. But they're out there, and I'm very pleased they're out there. And lots of water masers and some other molecules too, and there are a few lasers. So it didn't need invention. They were there all the time.
Do you think you can amplify gravitational waves just like a laser so that you have a grazer? And do you think this process is going on in the cosmos, amplification of gravitational waves, just like a laser action? And if so, would it be a quantum type of process which gives you amplification of gravitational waves?
Well, I think I can see how, in principle, gravitational waves can be amplified some, but I don't think it'd be significantly amplified or practically amplified. Really, quantitatively, very, very different.
All right. Given how much lasers can and still contribute to scientific research, do you think that the research into lasers as directed energy weapons is a waste of time and money? It's not like we're at all short of ways to kill one another faster and more efficiently at this point in our history. Why should we do it at the speed of light?
I don't get that.
Do you think of lasers being used in weaponry, basically?
What do I think of lasers being used for weaponry? Well, I'm rather pleased that lasers don't really hurt people very much. They're not really very good as weapons. They're useful in directing weapons. They're useful in navigation, very, very useful in navigation accurately, and directing weapons accurately and so on. And that's okay. I have no great objection to that. I think, unfortunately, we do have to have a military ability. But I'm glad they can't really hurt people in masses or very badly. I'm glad of that.
At least not now.
I noticed in your curriculum vitae that you had a prize for contributions to the understanding of religion. Could you comment a bit about that, sir?
This is your Temple Prize, contributions in understanding of religion. Can you comment on that?
Yeah, well, religious ideas are very important to me. The question is, what's this world all about? Why are we here? Why are we here? Why did it turn out this way, and so on? And I think science and religion can interact usefully in a sense. You see, we've discovered now, fortunately with the MESA, we've discovered there was a beginning to the universe. The universe had a beginning. Einstein didn't think the universe could have a beginning. No, that's quite completely illogical. It can't have a beginning. Well, it had a beginning. How? How and why? And the laws of science, we recognize more and more, have to be almost exactly the way they are for us to be here. Why did they happen to turn out that way? Well, some people want to say, oh, well, there's billions and billions of universes out there, and they're all different, and just one of them happened to turn out right. But why would there be all different physical laws? And are they really out there? We can't detect them. We can't prove that or anything. It's a supposition. I think religion and science can and should overlap and should help each other understand each other. And to me, religion is very important in my life. Very important to try to understand what is life all about, you see. Why are we here? What's it about? And I hope other people will be thoughtful about it too. They don't have to agree with me, my conclusions, but I think everybody ought to be thinking about these very deep, important, basic questions.
Okay, we'll take one more question.
Yeah, shifted back. Many of us in physics and mathematics are used to the idea, and our wives usually agree with this, that our best work is done before we're 30. And you seem to be overachieving. And I wonder if you have any comments on that. How come you didn't quit about when you were 30? Why are you still doing this at 95?
Well, actually, let's see. The Mason laser idea came along in 1951, and I was 36, so a little older than 30. Actually, young people are more exploring. Young people are more exploring and open. There's more openness there. I think that's one thing. I think older people should try to be more open. I mentioned the case of Niels Bohr and some others. You see, we need to be open-minded. Young people are more open-minded and exploring. They try different things, and they don't always work. It's okay. We need to explore, and maybe we won't find just what we want, but we explore hard and work hard. We're likely to run into something. Well, I think that's the difference between young people and older people. Young people are more open-minded and exploring, and they work hard. To me, I frequently say, well, I practically never work. I just do science. I have a good time doing science. And I like to continue. Why stop? It's such fun.
Well, thank you, Charles, and it is my pleasure as president of the Canadian Association of Physicists to present you with gifts from our organization. First, we have this PPhys t-shirt, professional physicist. We think you are certainly deserving of this t-shirt.
Thank you.
Wouldn't you say? Stand over here a bit so they can get a picture.
Thank you.
And secondly, we have, since we know Gerhard Herzberg's books were very important to you, we would like you to present you with this gift, which is written by Boris Stoichev, a very well-known faculty member at the University of Toronto who unfortunately perished not too long ago. And he wrote about the life of Gerhard Herzberg, and we would very much like you to have this
Thank you.
as a gift.
Well, I'm very, I'm very pleased to have this. Not only to admire Gerhard Herzberg, but also Boris Stoichev. They've been both very important to me.
And finally, some of you might have noticed the photo on the way in and a similar photo, in fact, the same photo, not quite so cropped, was shown up here in this slide of Charles some number of years ago. And we would like you to have this because this is the picture that we have used to promote our Herzberg lecture tonight. And we hope that you will enjoy this picture and that it has inspired all of us to keep doing physics until we are well into our 90s. Thank you.
Thank you. Thank you very much. Okay, great.
And I thank you for coming this evening. We now have a reception for you at which there will be coffee, tea, and dessert. Right after this talk, if you proceed out through the exits, our helpers in the red shirts, part of our local organizing committee, will direct you to where you shall go. Thank you and good evening.